Hello, everybody. Welcome back. We are still continuing with Module 7. This module is a very long module, and my intention is to get through a lot of Module 8, which regards to gas laws as well this week. So we've got our work cut out for us. Before we start, which we're going to start talking about solubility, I just wanted to clarify something. I made a little bit of a mistake in the last meeting with my limiting reagent problem, and I just wanted to point that out. If you notice, what I did was, instead of 0.350, I used 0.250. So instead of going through this whole thing and redoing it, what I want you guys to do is just read the problem a little bit differently. This is going to be 0.250 because that's what I actually did the problem for. It doesn't change the result, thank goodness, otherwise I would have to redo the whole thing. I still have sodium hydroxide as the limiting reagent, and based on this being a 250, this is the theoretical yield of the copper 2 hydroxide. So I just wanted to clarify that, and kind of wondering if anybody actually noticed. Any event, let's continue on. What we're going to talk about now is different types of aqueous solutions and solubility, which is a really important term in chemistry. So let's think for a moment about two very familiar aqueous solutions, salt water and sugar water. We know that salt water is a homogeneous mixture of sodium chloride and water. Sugar water is also a homogeneous mixture of sugar and water. If I take either salt or sugar and I stir these two substances separately in water, it seems to disappear. So what is the process of dissolution? What actually happens on that molecular level when these two substances actually form solutions? Remember, this is an ionic compound, and this is a molecular compound. Does that make a difference? Let's find out. All right, so what happens when a solute dissolves? There are attractive forces between the solute particles that hold them together. So there are these forces that are holding the solute together. There are also attractive forces between the solvent molecules. When we mix the solute with the solvent, what happens is I start forming attractive forces between the solute particles and the solvent molecules. So that's here. Now this solvent molecule is interacting with this solute. That's here. This solvent molecule is interacting with this solute particle. This is the key. If the attractions between the solute and the solvent are strong enough, the solute will dissolve. If they're not, the solute will not dissolve. So let's look at this some more carefully. Let's focus on water because we're largely looking at aqueous solutions in this module, right? There is an uneven distribution of electrons in the water molecule. This is a polar molecule. The oxygen side has a buildup of electron density. which gives us a partial negative charge on this side of the molecule. And then the hydrogen side has a buildup of partial positive charge because all the electrons are being pulled towards this oxygen due to the high electronegativity of the oxygen. Now, when sodium chloride is put into water, the attraction of my partial positive sodiums and of my fully positive sodium cations and my negatively charged chloride anions, this is going to compete, right, with water molecules in order for them to dissolve. So my partial positive sodium ions are going to be attracted to the partial negative parts of the water. My negatively charged anions are going to be attracted to the partial positively hydrogen part of water. These solute-solute interactions are going to be replaced with the solvent-solute interactions. And if this interaction is strong enough, then I will have a solution form. So think about this. Water is coming in and it's sort of bombarding the surface area of the salt. Each ion is going to be attracted to the water molecules and then pulled off and away from the crystal. When it enters the solution, the ion is going to be surrounded by water molecules, and it's going to insulate it from other ions. What happens when it totally dissolves is I get a solution with free-moving charged particles which are able to conduct electricity. Okay. So I'm sure everybody has heard of the idea of electrolytes and non-electrolytes. We're going to focus on the chemistry of this by describing electrolyte and non-electrolyte behavior in aqueous solutions. So in chemistry, electrolytes are substances that dissolve in water to produce conducting solutions of ions, whereas non-electrolytes are substances that do not produce ions in aqueous solution. So these are non-conducting because you need the ions in order to conduct electricity. This is sodium chloride, which is an ionic compound, dissociates into sodium and chloride, sodium cations and chloride anions. This is sugar, which is my molecular substance. And notice it dissolves, but I do not form ions. The entire intact molecule is dissolved in the water. When I look at conductivity, if I look at sodium chloride, if I have, this is the description here of this solution, sodium chloride, when dissolved in water, will conduct electricity because of the movement of charged particles, my ions. So if I form a circuit, my bulb is going to light because the electricity can still be conducted in this area here. If I look at sugar, however, right, it does not conduct electricity. It does not complete the circuit. I have no mobilely charged particles, so my bulb is dim, right? This forms no ions. Okay. There are two types of electrolytes that can form. I could have strong electrolytes. These are compounds that dissociate to a large extent when ions are dissolved in water. If I look at KCl, this totally dissolves. I have no solid. I'll just have a complete solution of ions. This will fully dissociate into potassium and chloride ions. If I look at weak electrolytes, I'm going to get a small extent of ionization when it's dissolved in water. For example, this is acetic acid. It's a weak acid. And when it's dissolved in water, I get a very small amount of the acetate anions and the H plus ions. So this will be very weakly conducting. Remember, acids are molecular compounds that will ionize when they're dissolved in water. The molecules are pulled apart by their attraction for the water, and when acids ionize, they form H plus cations and the anion of whatever conjugate base or polyatomic anion or anion that they were connected to. So this percentage of molecules that ionizes is going to vary. When I have a strong acid, I basically have 100% ionization. HCl is a strong acid. If I ionize just a small percentage of my acid molecule, I am a weak acid. And this is going to be something like HF. So HF actually has a few ions circulating in solution, but mostly it's intact HF molecules. Here, HCl almost completely dissolves into this H plus and Cl minus. This is actually pretty much gone, and I have an entire solution of ions, the H plus and the Cl minus in my solution. So when I have a strong acid, and there's only a few of them, you need to memorize these strong acids. Hydrochloric acid, HCl. Hydrobromic acid, HBr. Hydroiodic acid, HI. Perchloric acid, HClO4. Nitric acid, HNO3. And sulfuric acid, H2SO4. They are all 100% dissociated in the ions, so they're considered strong electrolytes. These guys are weak acids. They do not have dissociation. If I'm not strong, I'm weak. You need to memorize these strong acids because any other acid outside of these examples will be weak acids. If I have an ionic compound that is soluble in water, I have strong electrolytes. So these are soluble ionic compounds such as KBr, NaCl, sodium hydroxide, potassium hydroxide. Ionic compounds that are soluble in water are going to be considered strong electrolytes. Weak acids, any acid outside of these guys listed here are going to be weak acids. So you're going to memorize the strong acids, right? These are my strong acids. Those are the only strong acids we have, those 6, maybe HClO. Excuse me, some books mention HClO, which is hypochloric acid, as very strong as well. But if I'm not strong, I'm weak. So if I'm not one of these, I'm a weak electrolyte if I am an acid. Non-electrolytes. These are molecular substances, things that are covalently bonded and do not form ions. Those molecular compounds, other than strong or weak acids, are going to be non-electrolytes. You should be able to look at the structure of something to assess its characteristics and then determine whether it's a strong, a weak, or a non-electrolyte. There is a slight difference between these two terms, dissociation and ionization. If I have an ionic compound that dissolves in water, the anions and the cations actually separate from one another, which is called dissociation. So I have the sodium plus ions and the sulfide 2- ion in that ionic compound. Those ions are what's holding that lattice structure together, and they will separate or dissociate from one another when they are dissolved in water. If I have ionic compounds that contain polyatomic ions, my polyatomic group stays together and I get the cations and then my polyatomic anion staying together as one ion. Now, this is also a dissociation because I have the ions there already in that crystal lattice, but they are now going to separate from each other or dissociate to form their constituent ions, surrounded by water in the aqueous solution. If I have my strong acids, I don't have the ions to begin with. This is a molecular substance. So the process of dissolution actually ionizes those acids into the H+ ion and my anions. So there is a subtle but very important difference between the terms ionization and dissociation. Okay, now let's look at the solubility of ionic compounds. When an ionic compound dissolves in water, the resulting solution contains not the intact ionic compound. It contains its component ions that are dissolved in water. They're surrounded in water. But this is very important. Not all ionic compounds dissolve in water. For example, silver chloride remains solid and appears as a white powder at the bottom of the water. It does not dissolve in water. So we're going to use two terms to dissociate ionic compounds and other substances that dissolve in water or don't. If my compound dissolves in water, it's considered soluble, and if it doesn't, it's considered insoluble. Here's sort of what happens on a molecular, molecular view. Solid silver nitrate, when placed in water, will dissolve. It's going to dissociate to form silver+ ions in aqueous solution and nitrate ions in aqueous solution. This is what I see here. Both of those ions are going to be soluble and in the water and surrounded by those water molecules. If I look at silver chloride, which is AgCl, this remains intact. This does not dissolve. It's almost completely insoluble. So if I mix my solid silver chloride with water, virtually all of it remains as a solid within the liquid water. So how do I know when a salt is going to dissolve? Well, this is actually a rather complicated question. Predicting whether a compound will dissolve in water or not is not that easy. It actually depends on several factors. The best way to figure this out is to actually conduct experiments in order to experimentally determine whether a compound will dissolve in water or not. And then look at all the data to develop some rules. This is an empirical method. So this was done a lot in the lab over the years. And what we have is a set of solubility guidelines that allows us to look at a particular ionic substance and determine whether it's going to be soluble in water or not. So here are these guidelines. If I have group 1A cations or ammonium, now what is a group 1A cation? It's the metal, group 1A metal, right? This doesn't include hydrogen. Lithium, sodium, potassium, rubidium, cesium. They're supposed to lose an electron to become a +1 charge. If my compound contains one of these group 1A cations or ammonium, the only positively charged cation that's important in this class of chemistry, it will probably be soluble. Mostly it will be soluble. I also have probable solubility if I contain one of these anions. Halogens, halides, chloride, bromide, iodine, when they're anions and they're connected to some metal, they're probably going to be soluble. However, there are some notable exceptions. If a chloride, a bromide, or an iodide ion is attached to silver 1, mercury 1, or lead 2, this gives me insoluble compounds. If I have nitrate, perchlorate, acetate, or sulfate, I'm almost always soluble, except for if one of those ions, the nitrate, the chlorate, perchlorate, the acetate, or the sulfate, is combined with strontium, barium, mercury 1, or lead 2. These exceptions are important to note, and as a chemistry student, these solubility guidelines are going to be used often in the next coming weeks. If you intend to take Chem 2 in the fall or later on in your academic career, you definitely need to learn these and not be dependent on a solubility chart in order to determine whether these ionic compounds are soluble or not. This is a solubility chart. This is from one of the books that I have. Basically, the top part is a little different than the bottom part. Notice, I am soluble if I have a group 1A cation or ammonium ion, and there are no common exceptions. So if I have a lithium salt or a sodium salt or a potassium salt, I know that is soluble, no common exceptions. If I'm a halide, I have these common exceptions, which means these compounds are insoluble. If it's connected, if my halogen is connected to silver, mercury 1, or lead 2, that results in an insoluble compound. Now, these guys, nitrates, perchlorates, and acetates, no exceptions. I see a nitrate, it's soluble. I see a perchlorate, it's soluble. I see an acetate, it's soluble. But then notice here, if I have a sulfate, I do have these exceptions. Strontium, barium, mercury 1, or lead 2 will give me insoluble compounds. Now I go to the bottom of the chart. These start as insoluble. Carbonates are insoluble except when they contain a group 1A cation, which goes up to that rule. Sulfides are insoluble except when they contain group 1 cations and ammonium. There's also a couple. These guys will give us, right? Now these exceptions are soluble. Phosphates are generally insoluble except group 1A, which goes back up to our rule number 1. Hydroxides are generally insoluble except for my 1A cations. You getting the idea? If you know this rule, basically what you're saying is unless I have group 1A, all other carbonates are insoluble. Unless I had group 1A or ammonium, all other phosphates are insoluble. There are these sort of common exceptions, this calcium, strontium, and barium. Again, the exception on the bottom part is these will form soluble ionic compounds if they are hooked up with those anions. So what you need to be able to do is look at the formula of an ionic compound and figure out if it's going to dissolve in water or not. If it does, it's soluble, and if it doesn't, it's insoluble. Now, this is actually a matter of degree. There is a threshold, like so many grams per 100 mils, which sort of characterizes something as soluble. Things can be slightly insoluble, slightly soluble, sparingly soluble, or totally insoluble. So there's different degrees of solubility, but what you need to know is how to read this chart and apply it to various compounds that you see in the future. And here is where we're going to stop for this particular lecture. When we return, we're going to talk about applying these solubility rules to predict if I get reaction when I combine two ionic compounds, in the sense that do I form a precipitate or not. We're going to be looking at precipitation reactions and then other types of double displacement reactions as we go forward. I'll see you in a bit.